Hi, my name is Andrea Mejia. I'm a third-year graduate student in the Department of Physics at the University of Connecticut. And in this video, I wanted to discuss what electromagnetic form factors are. So before diving into this topic, here's just a quick overview of what I'll be discussing today. I'll start us off with what form factors are, followed by how they're measured, methods used to measure them. I'll provide some examples of form factors, and in particular, form factor for a nucleon, and then a brief description of some theoretical models we use to help study and describe form factors, and followed by and ending with a quick summary of everything that I discussed. So form factors are basically mathematical functions that quantify the distribution of various physical properties within a particle, particularly within the context of electromagnetic interactions. They provide insights into the internal structure of particles, and as I mentioned in the overview, they are used in theoretical models to better understand them and study them. And form factors are determined experimentally through processes like scattering experiments. And the deviations found in the scattering data from these experiments are encoded in terms of form factors defined through matrix elements of the electromagnetic current operator, which is defined here, where P prime is the final state of the particle with the final momentum, and the ket P is just the initial state of the particle with initial momentum P. And here's the definition, where Q is just the momentum transfer of the difference between the final momentum and the initial momentum. And this definition describes a spin zero particle such as nuclei. So how are they measured? So form factors are typically measured in scattering experiments. And scattering experiments are an important tool of nuclear and particle physics, and they're used to study the details of interactions between different particles and to obtain information about the internal structure of atomic nuclei and the constituents, such as nuclear sizes and shapes, that are undergoing a specific type of interactions, such as an elastic or inelastic collision. And so the methods used to measure form factors, let's consider an initial wave packet that's broad enough that it can be approximated by a plane wave with initial momentum p. And so the final state after scattering of that wave is determined by the propagator u, which is described by this operator S, which we'll call the S matrix. And so the probability of the particle entering the detector in the direction theta phi with opening angle d omega is the probability that the final momentum p of f lies in a cone of opening angle d omega. And so if we evaluate the S matrix of the U propagator to first order, treating the potential as a perturbation, the central potential being the target, the problem reduces then to the use of Fermi's golden rule, which tells us that the transition rate is just the rate of flow of probability into the opening angle d omega, described here in this formula. And so the transition rates, so the reaction rate, depends on the properties of the interaction particle potential described by, let's say, a Hamiltonian operator and the number of final states available, where W represents the transition rate from the initial to final state. M of Fi defines the transition matrix element of the perturbing potential, the interaction potential between the initial and final states, and rho of E prime is the density of the final state. And so the potential basically transforms the initial state wave function into the final wave function as described here. And so the golden rule basically describes the transition rate between quantum systems. So basically, in other words, the probability of how likely a quantum system is to make a transition from initial to final state in the presence of a perturbation per unit time. And so the connection between the reaction rate, the transition matrix element, and the density of final states is expressed by Fermi's second golden rule and applies to scattering processes. And so using Fermi's golden rule, we can use what's called the Born approximation, which provides a relatively simple way to calculate the scattering amplitude by considering only the first order term and neglecting higher order terms. And so basically it simplifies the description of the interaction between scattered particles by potential. And one particular condition that's necessary is that the target nucleus is heavy enough such that the recoil when the incident particle hits that target particle is negligible. And so this may not be accurate for strong potentials, however, it only is a good approximation for weak potentials. It's also not a good approximation for where the particle speed is comparable to the speed of light, so where relativistic effects take place. And so in scattering experiments, the cross-section is a fundamental quality that provides a measure of, of the likelihood or probability of a particular type of interaction occurring between particles as they scatter off one another. So it describes the ratio of the number of events over the incident flux. And typically, in the Rutherford scattering formula, the spin of the particle isn't involved. But for the differential cross-section, for the differential Mach cross-section, it does take into account the quantum nature of particles, which includes intrinsic spin, and provides a much more accurate description for particles with spin, such as electrons. And so experimentally, the magnitude of the form factor is determined by the ratio of the measured cross-section to the Mach cross-section. And so one therefore measures the cross-section for a fixed beam energy at various angles and divides by the calculated Mach cross-section. And so for a non-relativistic particle such as an electron scattering off a central potential, V of r, the Born approximation for the scattering amplitude, F theta phi, is often expressed as this formula right here, where Q is the momentum transfer vector of the scattered particle, R is the position vector in the scattering process, and V of r is the central potential. And so thus in this Born approximation, f of theta, f of phi equals to f of q is just the Fourier transform of the potential with respect to the momentum transfer right here, up to a constant factor. So some examples of form factors using the Born approximation method, which again neglects recoil, is basically the form factor is basically the Fourier transform of the charged function distribution f of x. So we expect that the form factors for point-like particles are constant, whereas form factors for non-point-like particles such as protons and neutrons are functions of the Mandelstam variable. And as far as we know, electrons are point-like objects without any internal structure, making it easier to extract information about the size and shape of the target nuclei, such as a proton and neutron, which does have an internal structure. So in other words, people do scattering experiments and measure the cross-section, which scatters point-like particles that have no structure off of something that does have structure. So the first measurements of nuclear form factors were carried out in the early 50s at the Linear Accelerator at Stanford University in California. And one of the first measurements of form factors that was done was of carbon-12, done by electron scattering. And so the figure to the left shows the differential cross-section measured at a fixed beam of energy at E equals 420 MeV at 7 different scattering angles. The dash line corresponds to the scattering of a plane wave off a homogeneous sphere with a diffuse surface, which is within the Born approximation, such as this. The solid line corresponds to an exact phase shift analysis, which was fitted to experimental data. And so the location of the minima, which is at approximately 51 degrees or so, thus tells us the size of carbon-12 nucleus. And so in this figure, in this table right here, it shows the relation between the radial charge distribution, P of R, and the corresponding form factor in the Born approximation. So for example, a constant form factor corresponds to a point-like charge particle, such as an electron, and a dipole form factor corresponds to a non-point-like particle, such as a proton, which falls off exponentially. And so information about the nuclear radius can be attained not only from the location of the minima of the form factor shown in the previous graph, but also from its behavior for Q squared as it goes to 0. So if the wavelength is considerably larger than the nuclear radius, the incident wavelength, the form factor can be expanded in powers of Q, where the, so shown here, where the mean square charge radius is defined by this formula. And in principle, the radial charge distribution, F of R, could be determined by the inverse Fourier transfer using the Q squared dependence of the experimental form factor. And so in this figure, we see a depiction of the radial charge distributions of various nuclei. These charge distributions can be approximated, described by what's known as a Fermi distribution, which I've left off here on purpose for the sake of brevity. And so, in other words, as we, the radial charge distribution can help determine the mean square radius, the mean square charge radius of a nuclei. And so here are some of the radii of different atomic nuclei. So as we have come to understand up to this point, form factors contains all the information about the spatial distribution of the charge of the object being studied. And so for nucleons, 2 form factors are necessary to characterize both electric and magnetic distributions. G of E as a function of Q squared, which is the electric form factor, and G of M as a function of Q squared, which is the magnetic form factor, where Q squared is the forward momentum transfer that is related to the scattering angle in experiments where particles are scattered by electromagnetic interactions. And so the measured Q squared dependence of the form factors basically gives us the information about the radial charge distribution. For example, in electron scattering experiments, Q squared is proportional to the momentum transfer from the incident electron to the target particle, as mentioned previously. And so the cross-section for the scattering of an electron off a nucleon is described by the Rosenbluth formula as shown here. In order to independently determine G of E and GMM, the cross-sections must be measured at fixed values of Q squared. In other words, at different beam energies E. The measured cross-sections are then divided by the cross-sections. And so an important milestone in the field of nucleon structure was actually brought on by the studies of elastic electron-proton scattering, where knowledge of the T-dependence of electromagnetic form factors allowed us allowed us to obtain information about the spatial distributions of electric charge and magnetization to be inferred, which led us to the first determination of the proton charge radius of about 0.74 plus or minus 0.24 Fermi. Theoretical models play a crucial role in describing and predicting form factors and provide a framework that helps interpret experimental results and help us understand the underlying physics that governs the distribution of charge, magnetization, and other properties within particles. So to name a few, here's some theoretical models commonly used in the study of form factors. Quark model, which describes the elementary constituents of nucleons called quarks, where form factors arise from distribution of quarks within the nucleons. Vector meson dominance model, which describes electromagnetic interactions involving hadrons, where virtual mesons mediate the interaction between the nucleon and the probing electromagnetic field. And then the QCB-based approach, so quantum chromodynamics is the fundamental theory describing the strong force between quarks and gluons, where lattice QCD simulations, for example, and other non-perturbative approaches aim to extract information about form factors. And so researchers use a combination of experimental data and theoretical frameworks to gain a comprehensive understanding of form factors. And so to briefly summarize things, electromagnetic form factors are functions that describe the distribution of electric charge and magnetization within a particle, such as a proton and a neutron. Methods used like the Born approximation under certain conditions can be used to simplify description of interaction between scattered particles. And measured form factors are measured via scattering experiments such as elastic and inelastic collisions that provide insights into their internal structures and the forces between particles. And in case you were wondering, this schematic here just describes the electron-proton scattering event, a cartoon version of it. So an electron scattering off of a proton with initial and final momentum. Thank you so much for attending my talk and listening to my video.